Hi, everyone. Welcome to today's session on hazard identification and risk assessment in a multi-hazard early warning system. In this session, we will explore the processes of identifying hazards and assessing risks, which are foundational for building a strong, effective early warning system that protects lives and reduces losses. Here are three key objectives for the session on hazard identification and risk assessment in a multi-hazard early warning system. Understand the process of hazard identification in a multi-hazard context. Participants will learn how to identify various hazards, natural, technological, biological, and human-made, that are relevant to a specific region, and how these hazards can interact in a multi-hazard environment. Gain insight into risk assessment techniques and tools. Participants will explore key components of risk assessment, including evaluating the likelihood and impact of hazards, understanding vulnerabilities, and using tools like GIS, risk matrices, and scenario development to prioritize risks and support decision-making. Explore the challenges and best practices in multi-hazard risk assessment. Participants will identify common challenges such as data gaps, changing risk landscapes, and coordination across sectors, and discuss best practices for improving the accuracy and effectiveness of risk assessment in disaster preparedness and response. Hazard identification and risk assessment serve several key objectives. First, we need to understand which hazards are relevant to the area, whether they are natural, technological, or human-made. Second, we must assess vulnerabilities to determine which populations and infrastructure are most at risk. By doing this, we can prioritize the risks that need the most attention, ensuring that we focus on hazards with the greatest potential for impact. Finally, hazard identification and risk assessment support informed decision-making by providing the data needed for preparedness, response, and mitigation. Hazard identification is the process of recognizing hazards that could potentially cause harm to people, property, and the environment. Hazards can be natural, such as floods or earthquakes, technological, such as chemical spills or industrial accidents, and human-made, such as conflict or terrorism. In a multi-hazard approach, we must consider the possibility of multiple hazards occurring at the same time or in sequence. It's also important to remember that hazards are dynamic and can evolve due to factors like climate change or urbanization, requiring continuous monitoring. In a multi-hazard context, we must be prepared for different types of hazards. Natural hazards include floods, earthquakes, tsunamis, and hurricanes. Technological hazards can include power outages, dam failures, or industrial accidents. Biological hazards have become especially relevant in recent times, including epidemics, pandemics, and diseases transmitted from animals to humans. Lastly, human-made hazards include conflicts, terrorism, and environmental degradation. Each of these hazards requires specific responses and preparedness measures, and they can interact with each other, compounding their impacts. Risk assessment is the process of evaluating the potential risks posed by identified hazards. It considers two main factors: the likelihood of the hazard occurring and the severity of its potential impact. But risk assessment doesn't stop there. It also analyzes the exposure and vulnerability of populations, infrastructure, and the environment to these hazards. By combining these factors, we can prioritize risks, focusing our resources on those with the greatest potential for harm. Before we proceed, we need to refresh our memory on the difference between hazard and risk. You may recall from Module 1 that the key difference between hazard and risk lies in the fact that a hazard is a potential event, while risk is the probability of that hazard causing harm. For example, a hurricane over the open ocean is a hazard, but it poses little risk to people or property. However, if the same hurricane makes landfall in a populated area, it becomes a high-risk event. In short, hazards exist independently, but risk is determined by how that hazard interacts with exposure and vulnerability. The risk assessment process is built on four key components. First, hazard identification helps us understand the threats we face. Next, we look at exposure. What or who is at risk from these hazards, including people, critical infrastructure, and ecosystems. Vulnerability assesses how susceptible these elements are to the hazard. Lastly, capacity looks at our ability to mitigate, respond to, and recover from hazards, which can significantly influence the overall risk level. There are several tools and methods we can use for hazard identification and risk assessment. Geographical Information Systems, or GIS, are essential for mapping hazards and identifying vulnerable areas, such as floodplains or earthquake fault zones. Historical data analysis can help predict future hazards by looking at past events. Scenario development allows us to create possible future situations based on current risk factors, helping us prepare for what might come. Risk matrices are a useful tool for assessing and ranking hazards based on their likelihood and impact, giving us a clear picture of which hazards require immediate attention. In a multi-hazard risk assessment, we must consider how hazards might interact. Compound hazards occur when multiple hazards amplify each other's impacts, such as flooding that follows an earthquake. Sequential hazards occur one after the other, potentially exhausting response capacity, like a drought followed by wildfires. Cascading effects happen when one hazard triggers another, such as an earthquake causing landslides or dam failures. Multi-hazard risk assessment requires understanding these complex risk profiles and preparing for combinations of natural, technological, and human-made hazards. Risk analysis is the process of identifying, assessing, and prioritizing risks in order to understand their potential impact and likelihood, ultimately guiding decision-making for risk management and mitigation. It is a crucial component in various fields such as disaster management, business, finance, public health, and safety. There are 5 key steps in risk analysis. 1. Risk identification. This step involves identifying all possible risks or hazards that could affect people, property, the environment, or systems. In the context of a disaster or multi-hazard early warning system, risks may include natural hazards, technological hazards, or biological hazards. 2. Risk assessment. Once risks are identified, they are assessed based on 2 main factors: likelihood, the probability that the risk or hazard will occur; impact, the potential severity of the consequences if the risk materializes. This step often includes a detailed analysis of vulnerability and the capacity to respond. 3. Risk prioritization. After assessing the likelihood and impact of each risk, the risks are prioritized. Risks that are both highly likely and potentially severe are ranked higher and require more immediate attention in terms of risk reduction or mitigation efforts. 4. Risk mitigation and management. Based on the analysis, strategies and plans are developed to reduce or mitigate the identified risks. This may involve preventive actions or measures to lessen the impact when the risk occurs. 5. Monitoring and review. Risk analysis is an ongoing process. Risks may evolve due to changes in environmental, technological, or social factors. Regular monitoring and reviews ensure that risk assessments remain accurate and that mitigation measures are effective. There are 2 primary approaches to risk analysis: qualitative risk analysis and quantitative risk analysis. Both approaches aim to assess and prioritize risks, but they differ in the methods they use and the type of data they rely on. Qualitative risk analysis is a subjective, descriptive approach to evaluating risks. It focuses on assessing risks based on their likelihood and impact using non-numerical data, typically through expert judgment, stakeholder input, and historical insights. Quantitative risk analysis is a data-driven approach that uses numerical values and statistical methods to assess risks. This approach aims to quantify the probability and impact of risks in measurable terms. Qualitative analysis is easier to implement, especially when precise numerical data is unavailable. It is also quicker to perform compared to quantitative methods, which can be time-consuming and data-intensive. Qualitative analysis is useful for high-level assessments or when the focus is on prioritizing risks for further analysis. Qualitative analysis can be biased or inconsistent, as it relies on opinions rather than hard data, and it lacks the exactness that quantitative methods can offer. Quantitative analysis provides a more accurate and objective assessment of risk by using hard data, and it allows decision-makers to understand the potential financial and operational impact of risks and the likelihood of occurrence. It is useful for complex risks where detailed data is available, providing more insights for planning and mitigation. Quantitative analysis requires substantial and accurate data, which may not always be available. It is also more difficult and time-consuming to implement due to the need for specialized tools and statistical methods. The analysis can be resource-intensive and expensive due to the need for advanced software and expertise. Now let's use a simple example to understand more about qualitative risk analysis. Imagine there is a small family farm with 1 ha of land. The farm is located on a floodplain and experiences regular floods. Here, we have a qualitative risk analysis using a risk matrix to assess the risk for a small family farm that is susceptible to a 5-centimeter flood. The farm is 1 hectare in size and has experienced 20 similar-sized floods in the past 100 years. In this case, we're asked to think about the risk based on 2 factors: the likelihood of the event happening and the consequence of the flood. Given the farm's location on a floodplain and its history of frequent flooding, we can reasonably assume that the likelihood of this type of flood occurring again is almost certain. Now, considering the consequence of a 5-centimeter flood on the farm, it is likely to cause moderate damage to the crops and perhaps some disruption to the farm's operations, but it might not be catastrophic. Therefore, we would categorize the consequence of the flood as moderate. Looking at the matrix, we can see that a moderate consequence combined with an almost certain likelihood places this risk in the high-risk category. This assessment informs us that this farm faces a significant ongoing risk from even small floods, and mitigation strategies should be prioritized to manage this frequent hazard. Using the same example, in a qualitative risk analysis for a potential 2-meter flood at the same farm. The key consideration here is that there have been no similar-sized floods recorded at this farm over the past 100 years, so we need to evaluate both the likelihood and consequence of such an event. Given that no 2-meter floods have occurred in the past century, we can categorize the likelihood of this event as unlikely. However, even though it's unlikely, we must consider the potential consequences of such a significant flood. A 2-meter flood could have severe consequences, including major damage to crops, destruction of infrastructure, and possibly long-term disruptions to the farm's operation. Therefore, we would categorize the consequence as major. When we combine the unlikely likelihood with the major consequence, we see from the risk matrix that the overall risk falls into the moderate risk category. This means that while the event is unlikely to occur, its impact could be significant, so it should still be considered in risk management and preparedness planning. Deterministic and probabilistic risk assessment are 2 distinct approaches used in evaluating risks. You can see the table comparing the differences between these 2 approaches. In summary, deterministic risk assessment is ideal when preparing for a specific known hazard or when focusing on the worst-case scenario. It is commonly used for disaster preparedness, where emergency planners need to ensure readiness for a particular magnitude of event. Probabilistic risk assessment is better suited for comprehensive risk management, where you need to evaluate the potential outcomes of multiple hazard events and prioritize resources based on risk profiles. It is commonly used in engineering, nuclear safety, and disaster risk reduction. After learning the different approaches to hazard identification and risk assessment, we must remember that while hazard identification and risk assessment are crucial, they come with challenges. Data gaps, whether due to incomplete or outdated data, can undermine the accuracy of risk assessments. Changing risk landscapes, driven by climate change and urbanization, require constant reassessment. Engaging local communities in the risk assessment process is essential, but can be challenging. With that, we have finished the session on hazard identification and risk assessment. When you are ready, please move on to the next session of Module 2. Thank you very much for your attention.